Welcome everybody. This is just to test the microphone and also people that want to jump in to hear that somebody is talking. Okay, close door. Thank you. So for those that they have not seen me in previous session, my name is Nico. I'm a major of Greece, IT specialized, and I've been working in the center in technical branch for the last 2 years. So our session has a very broad title. It's Anonymity, Privacy and Encryption, and that's on purpose because it's all of it. You see, it worked. Now they're coming in. So we'll try to explore some new attacks. First of all, I would like to mention that we have the app. So if you haven't already downloaded it, please do. There is also a survey there, so you can answer with few clicks some questions that we have, and will help us for next year. And also we have printed our proceedings. I know that they're nice to be a souvenir in your library, but 2 of our presenters actually have their paper there. So in case that you don't understand full the presentation or you have still questions, I need to be there, yeah, I forgot that. So you can read the paper. So I guess before our dinner you can read the paper. So I think it's time to start, and I would like to say that as already known, the mobile technologies need some kind of a function of fundamental to work. They need somehow to surveillance to know the location of the users. But on the same spot, we have also some kind of projects like Tor that are running, so people can be anonymized. And we'll also explore the legal aspect of use and abuse of the Tor. So let me introduce our panel. From left to right, we have Dr. Silke Holtman. She's working in the Bell Labs of Nokia, a security expert, 15 years. The last 10 years she's been in 3GPP security, and she has contributed in 3G and 4G security. She has written more than 50 security articles, books, chapters, and a book. But the most amazing for me is that she's inventor about of 100 patterns. Thanks you, Silke. So today she's focusing in the interconnection diameter, SS7, we'll talk about that, and network function visualization security. Next we have Dr. Paolo Palmieri. He's a lecturer of Department of Computing and Information in Cybersecurity Research Group at Bournemouth University. Bournemouth University in the UK. And of course, he has a PhD in cryptography. Last but not least, we have Mr. Thomas Inaric, our Thomas. He's working in the CCD COE in the Legal and Policy branch. He has a degree in the Charles University in Prague, expertise in criminal law and cybercrime, and lately his legal aspects and active responsible cyber defense and anonymity networks. So what is SS7 or signaling system 7? And is it possible for somebody that has access to telco backbone can take serious data from that, like the location or billing? So I guess we have an expert to answer to that. The floor is yours.
Thanks a lot. So it sounds pretty technical, but I try to keep it light. Not too many telco abbreviations, so I have a tendency to overstretch the abbreviation space. So first, this is a cooperation with a university, Aalto University in Helsinki. And also we were allowed to test the attacks or some of the attacks in the Vodafone test network in UK because we didn't want to wreck any sort of real network. which might impact your personal service if we did that. So let's start with it. So first, what is the roaming network? So we are now here in beautiful Estonia. So you have here 3 network operators. You have Elisa, you have Tele2, and you have TeliaSonera. Most of you are not from Estonia. So that means you have some subscription from Vodafone, from BT, from Hutchinson, or from some other operator. Now, you still can make phone calls here, which is a marvelous thing. So, but that doesn't happen exactly automatically. Because for that, this operator here, where you connect physically to the network, and your home operator somehow need to talk to each other. So, and this is not happening automatically. So this network where they basically talk to each other, or you can also sort of call it somewhat glue between the operator networks, this connects the whole world. So it's called interconnection network, IPX. So it's a really huge network. And maybe first a bit of history. It sounds a bit boring, but anyway, you need to sort of just get a brief grasp of the history. This thing is about 35 years old. It started with the Nordic mobile telephony network, sort of from the Nordic countries. It was a closed, private, cute network. We heard in the morning of the first steps of the internet, where there were something like 3,000 participants, and you just needed an email and a password, and you were in. So this is very similar, actually, in that sense that you just need to have access, and you're an operator, you're in. At the time this was created, the operators, most of them were state-owned, they were just a handful, they knew each other, probably studied even at the same university, the people, so they just knew each other. They just wanted to make it work so that the users would be happy. So they had this SS7 protocol. And what they did, okay, it was working fine, and then they started adding things for this service, for SMS, and then later on for data and others. Now things are moving forward, we take a new step, and that's called LTE diameter or 4G. This is also now coming also to the interconnection security. So you need to understand that about 8 billion subscriptions are connected in one way or to the other to this network. So, and it was built on trust. So how many people, how many companies are actually in that closed private network? So more or less 800 operators. And then we have large ranks of so-called service providers. That can be interconnection service providers, mobile virtual network operators. You probably have some in Estonia also, even if I'm not familiar with the names. And also most operators have a so-called wholesale business. That means they offer the connectivity to parties who want to rent it. Let's say for machine type applications or whatever. So the other thing is, do all operators connect directly to each other? That's a very important question, because how well do you know the person who sends a message? And in that case, actually not very well. Because the thing is that for economical reasons, it doesn't really make sense if, let's say, Estonia has a dedicated cable to Hawaii. It doesn't really make sense from an economical point of view. There are probably just a few phone calls per day, so it doesn't give enough money to justify putting a cable. So what they do, they make a contract with an interconnection provider. And this guy has then contract with 50 or 100 other operators. So these hubs or interconnection providers allow then for an operator here to offer roaming to hundreds of countries with one contract. So which is very efficient from a lot of management point of view. From security point of view, that's a nightmare. Because there's some message coming in and you get it from the interconnection provider, and okay, where is it really coming from? So it's a bit of messy, but let's go further. So this is very simple structure, how these kind of interconnection network might look like, just to give you some idea. So you have an operator A, you have some IPX providers, it's quite 2 or 3 is sort of quite normal. And then you have some operators. So if operator C sends something to operator A, it probably goes via IPX2, IPX1. But let's say if operator B sends something to operator C, it might take several routes there. So, and now imagine this picture with 800 operators. Then it's getting very funny. So just to give you an idea sort of how complex this network is and how difficult it is also to upgrade. So, oh well, there's some legacy. Okay, if I'm now an attacker, this is a closed network and I want to get in. What possibilities do I have? Well, I mean, we heard today that attackers have different kind of motivations. So depending on your background as a hacker, you either have a lot of social skills. That's from a presentation from KPN, this has actually happened to a European operator. And this letter basically says, I'm operator A and I would like to rent your wholesale access. And what they did, they used the name of an existing operators and just added the word telecom. And they had a working email with operator telecom and everything. And they know that 4 cases were, this letter was used. In 2 cases, actually, it resulted in signing of a contract. But they figured that out before they actually got hold of the access credentials. So that was really just stopped in the last minute. But it shows that this kind of social engineering also works in these cases. So, and that was an European operator. This European operator was then very progressive. It told other operators, hey, they tried this trick on us, so be aware that something is going on. So if you have social engineering skills, here you go. That's one way to get access. Well, in case you have hacking skills, there are other opportunities. Telco networks have thousands of nodes, and some are just badly configured. So on the top right, you see GGSN from a big Chinese operator, which is on the internet visible. If you hack that node, you have access to SS7. On the bottom, you have from an American operator, anonymous login open. I hope it's a honeypot. I really hope it. I don't know. So at least the upper one, it's definitely a node of the core network. With the lower node, I'm not 100% sure if it's really a core network or if it's some other node of AT&T. But anyway, so once you hack those nodes, you have access to the core network and can send messages to other operators, to interconnection providers. So basically, you can attack from those nodes a lot of other nodes worldwide. So, or if you just have money, you don't have social engineering skills, you don't have hacking skills, you just buy it. We saw already today hacking team, and they basically say that for something like 14,000 to 16,000 euros per year, you can have this kind of SS7 access and use it. And they offer it as a service. And I think, to my knowledge, hacking Steam is still in business. I think they have some restrictions nowadays. So if you have money, that's also a way to go. And actually, the prices have been confirmed. I have been not asking from them, but I have been sort of asking around the community what the usual prices are for this kind of access, and that's quite normal. So for the old technology, SS7, that you probably all use of you when you are roaming. So what attacks are known today? Eavesdropping, call redirection, which are actually quite complicated attacks. Message interception, SMS. This is particularly interesting in regard to the presentations we had this morning on two-factor authentication. A lot of two-factor authentication use SMS. And with message interception, you can intercept the SMS. So that puts a very strange light, especially on two-factor authentication. And I hope Swift is not using now two-factor authentication with SMS. I don't know, but let's hope not. IMEI whitelisting of stolen phones, because there's a register where stolen phones are listed. You can run an SS7 attack and it's no longer stolen in the database. Very nice if you want to sell it on the black market. You can track people on cell, region, country level. You can basically kick a user out of the network. Oh, well. And you can also pull down a network. There have been some oops like that during some testings to a Norwegian operator in spring. That was actually an accident. Credential theft, you can steal the authentication vectors and do, let's say, false base station attacks with 3G and 4G. Then you can have GRX attacks that are data attacks, which are a bit more complicated. Then you can have frauds, all kind of frauds. I'm not going into that because that might hurt seriously. And also recently the WhatsApp encryption. The encryption was okay, but the two-factor authentication of WhatsApp was basically circumvented because they used SMS as a confirmation code, and that was intercepted, and then they basically could gain access to the account. So, and this kind of wiretapping, you can also hire that as a service. If you are just, I mean, those companies are very service-oriented, let's call it that way. And this company, this Bulgarian company, it's working, as far as I know, have been confirmed by many people. So, but I don't know the price, so don't ask me. So, how you can track locations in 4G networks. This is now a bit more technical, but I try to keep it simple. So what you do is you're an attacker and you say, I'm your partner, I'm your roaming partner. I have a user here from you and I would need some data from him. Can you send me this data? So this is basically the insert subscriber data request. It's a very generic message and you cannot block it, because if you block it, the user cannot roam. And then there's no money, no roaming, no money, very easy. So this interface needs to be open. So you say, well, I'm a partner, please send me the user data. And your home network will be so nice and send you the user data. And if the right flags are set, then also the location information is going out. Now you see this line there in the middle, diameter routing agent, diameter edge agent. If you make that guy smart, then it knows it shouldn't send out any kind of location information out. Actually, some of the Nordic operators, they put a fake and dummy information in there. So I think they put everybody to the North Pole, which I think is a quite nice approach and quite nice solution to the problem. So, as said, you cannot block those messages because then you have no roaming, but you can do sort of tricks on the edge of the network on the diameter routing agent or diameter edge agent to protect the users. So, this is 4G and LTE, and it will also apply to 5G and IoT devices, so tracking of cars or whatever you think of. So, and the underlying problem with this interconnection network is that you don't know who sends you the messages. You cannot prove who sends the messages. It was built on trust. You don't know. So, how to make it better? Well, let's first sort of face the truth, what other attacks are there. You can also kick out a user from the network. For example, I can delete subscriber profile, I can update the location to nowhere, I can clear the location, I can perform some nasty frauds. Well, and I can also steal subscriber keys, which I then can put into a base station, into a false base station to do on-site interception attacks. So these attacks, some of them we confirmed in the network, the fraud attack, not because we didn't have a billing center connected to it, but the other ones we were able to confirm in test network. So you might say, so what, LTE security is crappy. That's not true. It's actually the interface is excellent security. It has a very good security mechanism, much better than 3G. So the LTE or 4G security is very good also for 5G. So from here to the network, no problem. The problem comes from the back end. So, and it's vulnerable if no countermeasures are taken. So you need to do something, that's all. So you might say, okay, location tracking, a bit of fraud for operators. So what's the problem for us? Well, it's not exactly only a privacy and consumer problem. There's a general trend for cost-saving reasons to use commercial networks also for public safety stuff. And there we come into trouble. What is a public safety group in a LTE network? Do you know that? Well, I can say it. You have the subscriber database, and in the subscriber database you have some fields saying this subscriber belongs to these subscriber groups. Now, if I can change this information, I can add myself or remove myself from a group. If I denial of service a network, I also pull down public safety network. If I run a denial of service attack against a particular user, I might sort of target some individual users that they don't get service, and those might be from public safety group. So it's not really only a consumer problem, it's also if you use it for public safety purposes, it's not only about the price you need to look if you ask for reference offers. You must also look at the network description. How do they protect their network? If they don't protect it, better build your own Tetra network. So you can do something. So for the old technology SS7, you can monitor the traffic. That's a good start, sort of trying to figure out what's happening in your network. And for the newer technology, you can put diameter edge agent and make them smart in the sense that they look at the traffic, they analyze the traffic. Sort of what internet is doing for years now, we still have to learn in mobile networks. Also, legacy partners, you have to think about that. In an African country, the third operator in a country, he will not be able to spend money on an expensive firewall. He doesn't have the money, he doesn't have the expertise. Well, you have to live with those partners. You cannot cut them off completely, so you have to find some other solution and try to classify traffic and see if it's malicious or not. And also there's some work in GSMA, that's the operator community, ongoing to define what are the problems and how to solve them. And also, if possible, use IPsec. It's not done today. So what are the obstacles? I mentioned some of them. If you go to an operator and want to sell them a firewall, they say, what's the return of the investment? Will the users pay more money for it? Unlikely. Then you have roaming partners, which just cannot or don't have the possibility to upgrade. Also, you have the interconnection providers. You remember the first picture with the cloud and the guys that were routing the stuff. Who is paying for the PKI, the operator or the interconnection provider? Interesting question. And also, I think we just have to live with the attack and see that we filter them out. So that's it. So hope I didn't bore you too much with mobile network protocols.
Thank you, Silke. Well, actually, if you read the paper, it's more detailed, and it's
a
lot of more.
There's the technical meat in the paper.
Yes,
so.
and there are a lot of attacks. This was a diagram for one, so I think it was 6 or 7, something like that. Yeah.
There are much more, but it sort of gives you an idea that this is a larger problem and not just affecting sort of one message or something. It's a big part of a bigger problem, and it will follow us for quite a while. So it's not something we can just patch and be happy.
So I don't know if you have any questions. Please.
Kado Huopio, NCSC Finland. I'm just wondering if you have done any analysis on the most prevalent smartphone apps and see how their security model breaks, or how their security model holds if there is a man-in-the-middle capability in the network.
No, we didn't do any sort of application-specific analysis. This was just sort of, okay, we can see that we get this data from the back end. So it was more sort of, what can you do if you are in the back end?
Yeah, I guess the WhatsApp is just the tip of the iceberg in a case.
But there, the encryption was not broken itself. It was really the two-factor authentication, and then you could get into the account and set up a second account, and then you got the chat history that was cached. So So the encryption actually still worked properly. It was just that you had access to the account. But basically it unhooks the security anyway. But it's a big warning towards all two-factor authentications which want to rely on SMS. So.
Somebody else? Okay, this sounds a little scary, isn't it? Yeah. So what is the operator are doing for that, or what European Union could do?
In the moment, the status is that Europe was basically the first regional area that took activity on this for SF7. And because there was in 2014 a bigger conference in Berlin where attacks were presented and working, then Asia had a similar thing because due to a CBS series where they showed live hacking of a senator. And there was a similar incident now in US, where the Federal Communication Commission is now looking into the issue. Basically, they should start with monitoring network operators, and from European Union exercising pressure that networks are critical infrastructure, mobile communication networks, and they need to be protected, like anything with firewalls in the internet. So mobile networks arrived in the internet for good and for bad.
So do you see a perspective that something is coming as a defense in the next years?
Yes, the first, I think that's also a question in the back, in the last
Okay.
one. So sorry.
Please. Yeah, you have to run. There was space here.
And I don't bite, really.
Hello, Lauri Korsberg from Cyber Defense Institute. I have a question: if the phenomenon of hackers, like starting tinkering with the LTE and building their own base stations, which can be seen like in the Chaos Computer Congress, has this influenced any way how those protocols are crafted, or are big telecoms actually taking into the concern?
The Chaos Computer Club conference had a presentation in December 2014, and based on this we started investigating countermeasures also, and also not only us, but also other companies started developing specific firewall products. And we try to find the attack in research before the attackers actually do. And we share them with the operator community and here with this community to show that they're really feasible, and try to put preventions in place before we are actually hit. So that's what we are trying to do. We will not be able to protect against everything, but we do our best.
Yeah. Okay. Thank you, Silke. I think the message was passed by to be aware of that. Thank you for that. This
Thanks
is
a lot.
Click and Grow, as always. An applause for you.
Thanks a lot.
Well, that was an attack, but also there is a defense. So there are also networks, probably Tor, if we use Tor on this kind of mobile networks. But are they really robust? Okay, Paolo.
Well, thank you for the introduction, and it's a pleasure to be here. So,
You can carry that with you. Yeah.
sorry?
Yeah.
So, anonymity networks, can they be a solution? Well, they can be a solution in a lot of scenarios, from mobile to wired network to wireless sensor network, Internet of Things. But is their current design effective, and can it be adapted to this sort of scenarios? Well, what I will be presenting today is an answer and a proposal for anonymity networks, and in particular one, the most popular, onion routing, for being adapted to distributed networks. So, onion routing is the protocol behind Tor. Probably most of you either used or heard about Tor. It's a software that allows you to browse the internet anonymously. The onion routing is the protocol that Tor implements. As a matter of fact, Tor stands for the onion router. Onion routing itself was proposed earlier than Tor. was proposed at the beginning of the 2000s, and it was later implemented, and it grew in popularity, and slowly it took, it basically got the most popular among all the anonymity networks. There are plenty of anonymity networks out there. Some are just theoretical experiments or proof of concept implementations. Some of them are actually being used. Apart from Tor, there's Freenet, which is possibly the oldest one, or one of the oldest ones that actually saw a good user base, a significant amount of users. There is I2P, there is GNU-net, which has very little users, but have some very interesting technical concepts. But both because it's technically sound and because it managed to attract a lot of attention, the most popular network being used now for anonymity on the internet is Tor. So let's see a bit how it works and what it aims to do. Well, what it aims to do first is to conceal the identity, the location, and the network activity of the user. The purpose of this is obviously to allow private communication over a private network, so over a public network. So the internet is a public network. When we browse to a website, when we send an email, the connection, the content that goes from our computer to the destination computer passes through a number of hops, and essentially there is no embedded inherent protocol that will guarantee the anonymity of our communication, so the destination will be able to see where the communication comes from. Anonymity networks are a layer on top of that can provide this sort of anonymity. How do they normally work? And how does onion routing work? Well, the idea behind most of, if not all, anonymity networks is actually to don't connect directly to the destination, but rather route the traffic, the content, through a number of hops. If the hops they're geographically distributed and they're quiet, so they will not reveal who is using them, well, then we can, let's say, disguise our communication, and the actual destination will see the last hop as a source of the communication rather than us. So in the onion routing in design, this is further expanded. In particular, onion routing works on circuits. So circuits are normally composed of 3 of these hops. In the onion routing, they're called relays, and they're servers whose job is essentially to relay the traffic. So when I want to send something over the internet, and by using Tor, instead of, let's say that I'm the red node, and that's me, and the green node is my destination, so for example, the web server I want to connect to, I will normally just, let's say, use, for example, directly the IP address of or the domain name of the destination. I will just connect to that node directly. If I use Tor instead, or onion routing, what will happen is my communication will first be sent to a first relay. The first relay will send it to a second relay, and the second relay to a third, and finally the communication will reach its final destination. But how is this secure? I mean, what makes this secure? Well, first, if this is implemented, we know that only the first relay will know the actual source of the communication. So only the first relay will know me, because I'm only talking to the first relay directly. The first relay will then talk to the second relay, and the second relay to the third relay, and the third relay to the destination, which means that the destination will be only known to the third relay. But how can we enforce this in practice? Because if they talk to each other, I mean, this cannot be guaranteed. The way it can be guaranteed is to use encryption, and essentially to use multiple encryption layers, so that every time that a communication goes from me to a relay or from a relay to another relay, only the 2 the two parties directly involved in the communication can communicate. This concept actually gave the name to onion routing because the layers of encryption that surround any packet are essentially the same as the onion, which is composed of different layers that you can peel off. And that is exactly what happens when the communication happens. So when I start my communication, I encrypt my message 3 times, 1 for each relay. I would then send it to the first relay, which will decrypt the first layer, and so that's to say, peel off the first layer of the onion, and will read the information that is directed to him. He will then pass it on to the second relay, which will decrypt a second layer, so that only information that is supposed to be seen by the second relay will be seen by him. The same applies to the third relay. So in order to achieve this, obviously, we have to distribute the encryption keys for the encryption. We also have to know which relays are available out there for us to build the circuit. And the way the current Tor implementation does this is basically creating a list, a public list of all the relays, of all the Tor nodes out there. And they've also flagged them with their characteristic. So for example, if a relay can be used as first, it will be signaled in the directory. This list is called a directory. If it can be used as last relay, and that's normally a fairly tricky task to have because it's the one that will deliver the communication to the destination. So the destination will actually see the communication coming from the third relay. It will be, so if the relay is available to perform this task, it will be again flagged in the directory. So this works, Tor works. You can build circuits, you can communicate anonymously. Of course, that depends, the security of it depends on the attackers, but the problem with it is that there is this list of relays. And why is that the problem? Well, first, if we want to, let's say, block some relays, for example, we don't want to accept traffic from the Tor network, we can easily do so. The list is public. We can just take all the exit nodes, so all the nodes that are available to be the third relay in the circuit, and we can just blacklist them. We can actually perform a DDoS attack, a denial of service attack. Tor is used by millions of users, but the amount of relays, so the servers, is actually fairly limited. It's only in the number of the thousands. And even more worrying, only a fraction of those thousands of relays available are able to sustain a large amount of traffic. So only a part of the network is actually at its core. Quite a good number of relays exist, and they do relay traffic, but very small amount. And the network needs powerful and fast nodes in order to operate. Another problem is, this means that we cannot go into any distributed sort of setting. So if we're talking about the internet, we can definitely make a public list of relays. But if we want to implement onion routing into a different settings, such as wireless sensor networks, that might become more difficult. And wireless sensor network is somehow a natural application scenario for onion routing. It hasn't been tested yet. This is not something that has been done, at least if it has been done, it's mostly being done at the experimentation level for the moment. But I've worked on implementation on onion routing in wireless sensor network, and it can provide some very useful features. For example, preserve context privacy. Context privacy is privacy of the network structure, the network topology. So for example, in wireless sensor networks, you need to, the sensor nodes, the nodes collect information, they sense information, and they basically gather this information on some of the nodes. These nodes are normally called base stations. it's very crucial, especially in hostile locations. If you have to deploy wireless sensor network in hostile locations, it could be a battlefield, for example. It's crucial for the base nodes to be secret, not to be identifiable, because they will be obviously the main target of any attack. But the nodes still need to communicate to those base nodes. Implementing onion routing could provide a layer of protection and anonymity inside the network so that these base nodes can remain secret within the network. But in this context, having a directory of lists, a directory of nodes that operate as relay is probably not practical. The same applies to the Internet of Things and other application scenarios, right, such as the cryptocurrencies. So why isn't it practical to have this directory of nodes? Why do we need a more distributed network? This is essentially the point of my presentation. I mean, moving onion routing from a more centralized structure into a more decentralized structure. Well, essentially, any sort of network, such as wireless sensor network, any sort of network that is that can be deployed, that need to be deployed quickly, any network that have nodes that can enter the network and exit the network without disrupting the network operation, needs to have some sort of decentralized structure. I mean, peer-to-peer networks provide exactly these useful features. In peer-to-peer networks, you have nodes that can enter the network at any time, exit the network at any time. Nodes can be on and off, they can connect, and the network should continue working. That is exactly how a peer-to-peer network works. This sort of operation is currently impossible in the Tor network. Relays take days before they attract enough traffic. So if I set up a new relay on Tor, I will first have to communicate my information to the directory list. The directory list will start advertising this information after a while, and then only after some more time will the network actually start using my relay. It takes a long time. It's normally about 7 days before a relay goes to full capacity and starts routing information. If we have a sensor network, let's say that we want to sense during a flooding, we just want to deploy sensors in a flooded area or in a battlefield. We need to be able to deploy more sensors or take some sensors off or just disable some in a matter of minutes, definitely not days. So what can we do about this? Onion routing doesn't imply per se a centralized network structure. This is how it has been implemented in Tor. But it can be changed, and the rest of my talk will basically be a proposal on how we can achieve, a first proposal on how we can achieve this change from a structured topology into a more decentralized and peer-to-peer topology. So what are the assumptions that make it difficult? Why can't we just immediately implement onion routing in a decentralized network? Well, there are two main assumptions that are done in the current onion routing usage, and especially on Tor. The first assumption is that all the network's nodes are basically able to communicate with any other network node. So they have, in technical terms, full visibility of the network. So any relay in particular, not necessarily every user, but every relay should be able to communicate to any other relay. So when I go and build a circuit, this path of 3 relays in a row, I don't need to check whether the first relay can communicate to the second one or the second one to the third one. This is an assumption. The second assumption is the presence of this directory structure. And the assumption there is not only the fact that the directory structure exists, but also that it can be created and it can be maintained. Which means I need to know every time a network, a new relay is created, and I need to be warned when a relay goes down. Otherwise, I might just create faulty circuits. And if I create these faulty circuits, I will definitely be able to understand that, and I might create another circuit, but the overhead is, for the network is problematic. And so, in order to address these issues, my proposal is to create a sort of data structure that will allow any node to, well, let's say, communicate to other nodes which circuits it can build and which circuits it cannot build. Essentially, which nodes it can connect to and which nodes it cannot. If this is possible, and if we can do it in a privacy-preserving way, so without essentially giving up too much information, well, then we solved most of the problems. Because if that is possible, we don't need the directory structure anymore. And we can guarantee that every time we build the circuit will not fail because two nodes cannot communicate. It might fail for other reasons, but not because of visibility reasons. So we call this structure the visibility filter. And the visibility filter, the name filter comes from Bloom filters. Bloom filters are a data structure that are quite interesting. If you haven't heard about them, you probably use them. They're used in a number of scenarios. They're a data structure that is very space efficient, so it only takes very little space to store a lot of information, and it's a data structure that is useful for set, any sort of set operation. In particular, membership queries. Membership queries are when we ask a set, is this element in the set or not? How do Bloom filters work? Bloom filters are based on hash functions. So, from the image, if I have a number of elements, let's say 10 elements, to keep it simple, I want to encode, and these are elements of a set, I will want to create a filter, a Bloom filter of this set. So that instead of giving away the elements themselves to people, for them to be able to query whether an element is in the set or not, I can just give the Bloom filter, and the people will be able to query the Bloom filter instead. The properties of the Bloom filter will make it fairly privacy preserving. Additional privacy can be added by encryption, but already the Bloom filter structure is already fairly privacy preserving. How does it work? In very simple terms. I know it's late and everybody wants to go to dinner, and more details are in the paper, but in very simple terms, the way it works is a Bloom filter is a binary string. So a lot of binary, a long string of binaries. Their start, when I'm creating the filter, they start all as zeros. The length of the string is the same as the output of the hash function. The output of the hash functions means that my hash function, for example, if it has a length of, well, 2, then it will only give me either 1 or 2 as a result. So any input I give to the hash function, it will either give me 1 or 2, depending on the length. So the length of the filter will be the length of the output of this hash function. I can decide it. And the decision will be based on essentially how many elements I want to input into the filter. For any element, I will essentially encode it through different hash functions, all with the same output. Each element for which the hash function gives the result, I will set it as 1 in the filter. And I will do that for each of the elements of my set. If I do that, I will be basically, the result of this operation will be basically a string with zeros and 1. And the way I can query the filter is simply encode through the hash functions the element I want to test, and check on the filter if the corresponding values are all 1s or are not. If they're all 1s, it means with a good probability, there is some false probability, that the element has been encoded in the filter. So the 1s are there because the hash functions were wrote the 1s because that element is part of the filter. If I find even just 1 0, it just means that the element is not in the filter. What we can do with this is essentially use the same concept to encode nodes in the network. So we will create visibility filters, and what we will put in the visibility filters is the networks, the nodes each node can communicate with. We will then distribute these filters through a controlled flooding. So each node will create a filter, input in the filter all the nodes it can communicate to, and just flood these filters in a controlled manner. So it gets distributed across the network, but only up to 3 or 2 steps, depending on the size of the network. Once we have done that, I will not go into the details also because my time is finishing, but the onion circuit creation will be modified so that the nodes can use these visibility filters to check whether they can connect to a specific node on the network. And therefore, each circuit will be built only on nodes that can communicate with each other. So each node will be able to independently test whether they can communicate with a different node or not. The performance of this scheme is fairly good. In terms of overhead, we are talking about hundreds of bytes if we assume around 100 nodes in the neighbors. Neighbors are basically nodes that are directly connected to the original load. And this is for a very small false probability. So I'm going to conclude, and essentially this new method I'm proposing, I've now briefly presented, is aimed at making onion routing possible over distributed networks. And distributed networks have application scenarios in a lot of domains which are currently excluded from onion routing because of the constraints that we have seen. So by using this method, we will be able to implement onion routing on a lot of scenarios where it currently is not possible. That concludes my talk.
Thank you, Paolo. I don't know if we have any questions. You tried to be very abstract. Okay, we have questions. That's good. So that means that you understand something.
Hi, my name is Dmitry Smirnov. I'm from Estonian Cyber Defense Unit. And well, one of the remarks, you've noticed that Tor relays take quite a lot of time to get added to the directory. But as far as I remember, that is a countermeasure to the very widespread and well-known attack carried out by the Chaos Club by inserting rogue nodes, especially with quite cheap commodity cloud powers. You can flood the Tor network with your own nodes that will give out all the information of the data that is passing through them. Aren't you afraid that by limiting the visibility, introducing filters, you will make this kind of attack much easier on the network with these filters?
This is a very good point. So in any network, and especially peer-to-peer network, but also in Tor, you can fall victim of what is called the Sybil attack. So basically, as an attacker, I flood the network with a lot of nodes which I run directly, and I will just use those nodes and hope that my victim will basically build the whole circuit on my nodes. There are so many, there's such a good portion of the network that I have a good probability of the victim just using only the nodes I directly control, and therefore there will be no anonymity. This is true also in all sorts of scenarios. what we propose, I mean, the mechanism we propose, and there are details in the paper, essentially ensures that when building a circuit, you don't use nodes that are only in your vicinity. So you try to go as far away as possible. This is one of the possible defenses from this kind of attack. In practice, it's almost impossible to prevent an attack like that, because if an attacker is well determined and he will just keep inputting nodes into the network, at some point he will just have the majority of the nodes in the network. You can try to limit the speed at which the nodes can join, but if they create just enough nodes, they will have the majority of the network. So we have to have the assumption that at least a majority of the network nodes are not malicious, or at least if they are malicious, they're not cooperating with each other. So if I have two different malicious nodes, the circuits are still secure as long as the two nodes are not cooperating with each other. So if we have multiple attackers doing the same attack, well, then we might actually be safer than one single attacker flooding the network with the nodes. But yeah, that's an open problem, and it's fairly difficult to address, especially when the number of relays are limited.
Thank you.
Universität der Bundeswehr. One question. The distribution enables a quite dynamic usage of the Tor network, but the anonymity of the Tor network relies strongly on the lengthy part of the entry point. So you can't change the entry point as quick as the mid and the exit points, what you do on an interval of 10 minutes by default. So have you done some simulations how the level of anonymity is influenced by introducing these dynamic structures?
So the entry points are, it's a very good point, and the entry points are normally referred as guard, and just as background information, they're normally flagged, and they're very limited number, and those are some sort of nodes that are more trusted than regular nodes, so they've been running for a long time, and they're considered fairly stable. And this is another countermeasure to an attacker trying to flood the network with new nodes. So of course, this is not possible. I mean, listing some nodes as entry nodes is not possible in a distributed setting. However, when in a distributed setting, you only have visibility of a number of nodes, then you have to accept that you can only connect to those nodes. If it's a distributed network, I don't have visibility of nodes that are too far away from me. So even if I was able to flag those nodes as entry guards, I wouldn't be able to connect to them. And this is the first step in the circuit, so it's quite problematic. I've done some simulations, but those are for things like wireless sensor networks, which normally have a very limited number of nodes. So the main problem there is not actually having malicious entry nodes, but rather keeping the whole overall network topology secret. So if you're talking about smaller networks, such as wireless sensor networks or such as some Internet of Things applications where we have a few thousands of nodes, and I'm not talking about relays, but in this case, nodes are users. Well, in that case, my opinion is that you don't necessarily need the construction of guard nodes. It's actually better for security to be able to connect to any node on the network you can connect to, rather than being limited to a small number of nodes, such as 10 nodes, which will obviously become the first target for an attack, for example, a DDoS attack.
Okay, Robert, unanswered question.
Thank you. You said in the end you will have about 100 neighbors. Does it mean that the build circuit will be quite locally distributed? Because that will ease traffic analysis attacks very, very much.
Yes, so technically in the paper, in the construction, we actually make sure that it's not local. So we actually make sure, using the visibility filter, that the first node in the circuit, so the first relay, is not a neighbor of the third relay. This ensures that the circuit it goes as far away as possible from the originator. So through the visibility filters, we can actually check, for example, if the first relay is a neighbor of any of the relay. And we can actually, through the visibility filter, select relays that are not neighbors. So if I'm an attacker, this makes my attack much more costly because I need to distribute malicious nodes all over the network rather than just localized around the user. So this is another defense from a Sybil attack. So trying to make the circuit as lengthy and as far away as possible from the originator. So a potential attacker needs really to deploy nodes all over the network rather than just in the area where he thinks the targets will be.
I hope you don't have another question because they will all blame you for the dinner, you know? Okay, I have to thank Paolo because first of all, it's a paper that is novel and we are missing this kind of papers in our proceedings. And I hope the Tor community will consider about this problem on DDoS attacks against Tor. But if it doesn't, then you can be a gardener also. So I hope it will be a start. Thank you. Okay, an applause, just to be more energetic. So most of you have already thought that, okay, why we're looking about Tor? And is it, we shouldn't, because everybody in Tor is thinking about crime. And this anonymity is not good. Well, let's see how the legal aspect of the Tor, of use and abuse, and what the governments are actually doing. I mean, this DDoS attack can be also from other aspects. So we have Thomas here. So the floor is yours.
Thank you. So, yeah, it's there. Okay. First of all, I would like to thank Nico for the invitation to this panel. I'm very happy to be here and to be able to present our research. I was also listening with some interest to the other presentations because, as the president noted in his panel, it's very important for lawyers and policymakers to listen to the techies and vice versa in order to learn from each other and be able to do our research. In case you're wondering about the title, it's a paraphrase of a widely known classified presentation by a certain government which said Tor stinks, meaning it was difficult for that government to track Tor users. So it looks that it obviously bothers certain branches of certain governments, and that's why we became interested in the topic for our research in the law and policy branch of the CCD-COE. So this is the structure of my presentation. I would like to walk you through the basics of Tor, even though Paolo explained the technical side of things really well. Then I will focus on the users, who they are, what they do, what rights they have, what laws they break. Then I would like to talk a bit about the exit node providers, because that's let's say the backbone of the network, because they provide the interface between Tor and the rest of the internet. And finally, I would like to look at some of the aspects of government and their policies towards Tor. So, yeah, this is a familiar picture by the Electronic Frontier Foundation, which should show to the non-techies how Tor works. I will not explain the technical details, but I would like to point out three things that are important for the legal analysis. And the first one is Tor is an anonymity tool. It's protecting the user from being discovered communicating with other people or accessing certain websites. So for those of us who are not techies, it changes your IP, and if somebody hacks some of the proxies on the way, he cannot really tell your original IP address anyway. So that's sort of an improvement over a normal proxy. The second purpose of Tor is to defeat censorship. So if you live in a country or if you stay in a country that blocks certain websites from you, Tor can serve you to connect to websites that you would be otherwise unable to access. So it enables users to bypass web censorship. And third point is that even though the anonymity provided by Tor is based on 3-level encryption, it does not provide end-to-end encryption by itself, by default. So it protects the metadata, not the content. So unless you have an additional layer of encryption going out of the Tor, then somebody who's in control of the exit node can still eavesdrop on your traffic. Of course, sometimes the traffic never leaves Tor. This is an example, the old site of the Silk Road, which was hosted as a Tor hidden service. Inside the Tor network, it was an illegal marketplace offering drugs and other illicit material. But still, even in this case, the FBI was able to seize this site and get hold of its operators. So, but the point is that soon after that, Silk Road 2.0 was online. It was seized sometime later. Now we have Silk Road 3.0 and multitude of other marketplaces. I will not point you to any particular ones, but yeah. So who actually uses Tor? It's apart from terrorists, spies, drug dealers, child porn users, well, other criminals. Tor is also used by human rights activists and people who try to bypass censorship, witnesses to serious crimes, whistleblowers and journalists and their sources, but also government officials, law enforcement, military. So is Tor actually good or bad? Well, it's a technology. As most technologies, it can be used for good and bad purposes. And what can the governments do to help? Well, they can take four different policies. Sometimes they take several of them at the same time. They can support Tor, like the United States, which provides funding to the Tor project. In 2013, they provided $1.8 million for the research. They can also help them in other ways, like informing them of vulnerabilities. That's another way. Some governments, however, don't have such a good relation to Tor. They suppress Tor or they try to ban it. Tor is, according to my information, banned in China. Also, the French government was exploring the options to ban open Wi-Fi and Tor after the November 2015 attacks. So there is something to be wary about. In other countries, Tor is simply blocked or suppressed. China, Saudi Arabia, the Emirates, Iran, many other countries. So there's always this arms race between the Tor team and the governments that are trying to block it and to outwit each other. Other governments are trying to crack Tor. Of course, you probably know about the NSA, who tries to get at the users. They track users who are believed to live in the US, who are believed to live outside the US and who request Tor bridge information or they download the program. The NSA is also in control of some exit nodes. Nobody knows how many, but it is widely known that it is in control. Also, for other countries, Russia offered a reward of around $110,000 for anyone who can crack Tor and identify the users. But that was back in 2013, so I don't know if that price tag is still there. So we decided to look at the legal aspects and write an article. And we got it published in the Computer Law and Security Review in February with Anna Maria Osula, who you probably know as the lady who was introducing the speakers in the morning. Yeah, if you are interested in reading this article and you don't have the access to Science Direct, I can provide it directly to you if you want by email. If you don't have the time or are not interested, I can try to sum up our findings in the upcoming slides. So first, we looked at the idea of anonymity, both online and offline, and we found out that it's beneficial or even necessary for the benign users. Anonymity is necessary for some people, like the investigators of serious offenses or lottery winners. In some countries, voting is compulsorily anonymous. So we considered if there was a right to anonymity, and we found out that anonymity is probably not a separate right, but rather a necessary component of other human rights. Because sometimes you need to identify people for good reasons, such as for getting them to pay the taxes or register their purchases of real estate. And there are several declarations about anonymity by international organizations like the Council of Europe. That's the organization that drafted the first conventions on personal data protection and on cybercrime. And it's remarkable that already in 2003, the Committee of Ministers said that in order to ensure protection against online surveillance and to enhance the free expression of information and ideas, member states should respect the will of users of the internet not to disclose their identity. This does not prevent member states from taking measures and cooperating in order to trace those responsible for criminal acts in accordance with national law. This was picked up by the other organization, which is the United Nations, a little bit later. But still, before, let's say, the big thing, which were the Snowden leaks, this is from a report of Frank Larry, the Special Rapporteur on the promotion and protection of the right to freedom of opinion and expression, where he said that in order for individuals to exercise their right to privacy in communications, they must be able to ensure that these remain private, secure, and if they choose, anonymous. Restrictions on anonymity facilitate state communication surveillance by simplifying the identification of individuals accessing or disseminating prohibited content, making such individuals more vulnerable to other forms of state surveillance. And a more recent report on encryption and anonymity from 2015 reiterated that because of the importance to the rights of freedom of opinion and expression, restrictions on encryption and anonymity must be strictly limited according to principles of legality, necessity, proportionality, and legitimacy and objective. So the discussion is focusing on human rights, 3 of them in particular: right to freedom of opinion and expression, right to privacy, and the EU-specific right to the protection of personal data. First one, the right to freedom of opinion and expression, is covered by several international treaties, starting with the International Covenant on Civil and Political Rights, also the European Convention on Human Rights, and the non-legal document, Universal Declaration of Human Rights. I won't go through the wording of the documents, but we can say that one of the applications of this right is the protection of communication between journalists and their sources. And as you probably know, Laura Poitras was using Tor while communicating with Edward Snowden when he was whistleblowing on whatever he thought was inappropriate. Of course, it can be limited by law. Again, I won't go through the wording of the provisions, but I'm sure you're familiar with the fact that states try to regulate defamation, illicit pornography, copyright infringement. These are all accepted limitations of the right to freedom of opinion and expression. But as we know, a lot of bad stuff is going on in Tor. Dr. Thomas Reed co-authored a recent study which states that the majority of Tor is used for criminal purposes. So could we actually ban Tor or effectively undermine it by regulating the encryption, as some politicians try to suggest? And we argue that a ban on Tor or trying to undermine it would be an unjustifiable interference with the right to freedom of expression and opinion, because it would not pass the proportionality test. The law would be unsuitable for its purpose. It would not remove the dark websites, it only make them harder to access. The ban would be technically unenforceable. Also, the ban would not meet the necessity criterion. There are other ways to stop dark websites which are less intrusive into human rights. And it would not meet the condition of proportionality in the strict sense, because the government would have to prove that instituting the ban can reduce drug trafficking, child pornography, or copyright infringement to such an extent that it outweighs the loss of anonymity for benign users. And there is no research to support that. And actually, the UK Parliamentary Office of Science and Technology in 2015 stated in its report that it has been argued that online drug markets like Silk Road transfer parts of the drug dealing business from the streets to the internet and may shorten the supply chain from drug producers to consumers. And some say that this can reduce the number of drug-related crimes like robbery and shoplifting, and thus lower the social and economic costs of drug misuse. The situation with the right to privacy and protection of personal data is similar. These are also, or the right to privacy is also covered by the same documents as the previous right. And also it can be limited by the law for similar reasons. For example, certain measures during a criminal investigation or intelligence operations can legally interfere with the right to privacy. Nevertheless, such measures must be taken in accordance with a clear and accessible law. They must be proportionate and necessary in a democratic society. And this is what states don't always care about. The United Nations High Commissioner for Human Rights stated in her report from 2014 that practices in many states have revealed a lack of adequate national legislation and or enforcement, weak procedural safeguards, and ineffective oversight, all of which have contributed to a lack of accountability for arbitrary or unlawful interference in the right to privacy. This was picked up by the Court of Justice of the European Union, which stated in repealing the data retention directive that anonymous communication limits the ability of data retention measures to attain the objective pursued. It is not, however, such as to make that measure inappropriate. So this is following the idea in the Frank Larue report, or to put it more simply, we can perhaps quote Bruce Schneier or paraphrase Bruce Schneier that even though nobody is safe from targeted surveillance, ubiquitous encryption and anonymization helps protect against mass surveillance. And the more people use encryption, the higher the cost of mass surveillance. Similar thing for the protection of personal data. In the Schrems case, the Court of Justice of the EU ruled that in the safe harbor decision, the European Commission was unable to prove that the US ensures an adequate level of protection. So people who care about their privacy and use Tor, and perhaps combine it with encryption, like VPN, can lead to governments reallocating resources from mass surveillance to targeted surveillance, which is probably the long-term goal. So the bottom line is that governments should not ban or block Tor due to human rights regards, and they have to find more subtle ways to deal with the abuses, which should limit the impact on normal users. So now we're going on to the exit node providers. These are vital for the functioning of Tor, as I noted in the beginning. Can you actually get arrested for running an exit node? That's a question which is asked by people who want to do this. And the question is, yeah, it depends. Depends where you go and what you do. But there's an interesting case from Austria. Now we were focusing on the EU and Council of Europe member states for our analysis. This Mr. Weber, he was remotely operating Tor exit nodes from Austria, and some of those nodes were used for downloading child porn. And in 2012, the police came knocking on his door, and he was convicted in June 2014 and did not appeal the verdict. However, the court did not deal with the question of whether he was responsible for the content transferred. He sort of made the error of posting comments online saying stuff like, if you want to host child porn, I would use Tor. The court sort of thought that this made him liable for whatever activities he was doing. So this caused a bit of a panic among the Tor exit node providers, but actually the question is whether, if you do not do anything harmful or bad, are you responsible for the traffic that passes through your exit node? And according to the e-commerce directive and other EU documents, service providers are not liable for the information transmitted if they act as a mere conduit. So they just pass the information on. They do not look at it. They do not filter it. They do not do anything. And in that case, they would not be liable. However, according to the e-commerce directive, the information society service is any service normally provided for remuneration, so something that you pay for. And this complicates things a bit because Tor exit node providers usually don't charge money for the use of their equipment. Yeah, on the other hand, there is no reason to treat them differently from the paid providers. So we tried to look for analogies. So we found that this very question was posed to the Court of Justice of the EU. There is a case of Tobias McFadden, with the ruling still upcoming. And it's concerning open Wi-Fi, which, according to our analysis, shares the fate of the exit nodes because it's also provided for free, and it's not certain whether it can be covered by this particular provision. But fortunately, according to the opinion of the Advocate General before that court, from March 2016, the free open Wi-Fi is covered by the mere conduit. So that gives us some hope that the court might extend this to the Tor exit node providers as well. And finally, we're going over to the final part, Tor and governments. There are just a few things that I may mention that are perhaps worth looking at by researchers who are interested. For example, the personal data protection. Right now we had this reform in the EU with a new directive, new general data protection regulation, and a directive on personal data protection in law enforcement. So that might give some problems to law enforcement in dealing with Tor. Also, when law enforcement tries to intercept traffic at the exit nodes, that's another interesting issue because the Tor circuits change every 10 minutes, and it's very difficult to run through the whole process of applying for a court order and being able to intercept the traffic at the exit node at this time frame. So I don't know how they do it actually in the countries. There are, of course, also international law issues like the Lotus principle, like the exercise of jurisdiction based on the Lotus principle, state responsibility, sovereignty, these kinds of things. And also there have been some developments I think in the US where they are trying to push a legislation that would allow investigators to hack to Tor users' computers without the knowledge of their location. So I don't know how that will develop. So as a summary, governments have ambivalent policies about Tor. The trends are going in all directions. But I guess that Tor is here to stay. It cannot be easily banned or suppressed, both locally and on the global scale. The enforcement of such a ban would require an overhaul of the internet and derogation from several universally accepted human rights. Nevertheless, the status of exit node providers is still uncertain, but there is hope, as I said. And yeah, that concludes my presentation. Yeah.
Thank you, Thomas. Any questions? Do we have any questions? Please.
Katohopio, NCSC Finland. My concern with the Tor exit nodes is not is purely technical in a way, or I would say information security one. We have seen a significant rise of, I mean, technically malicious activity, not copyright infringements or something like that, but really malicious activity originating from Tor exit nodes to the public internet, targeting individuals or organizations. And examples would be, say, SSH brute force attempts, or really trying to hack into systems using Tor. And this is a dilemma if one thinks of the good uses of Tor, because these are really factors that actually force action to be taken against exit nodes, because they are the known originator of this malicious activity. And from the victim point of view, that is the target of this malicious activity, they want this activity to stop. And the only way to stop is to remove the exit node. And we are in a very big dilemma of actually how to deny use of Tor for really technically malicious activity, and to allow the other, I would say, good uses of Tor. And this is something that the Tor community really should start considering more.
The question is legal?
Well, it's
ethical?
It's a legal question in a way that it's technically
Maybe Paolo can answer
traffic that is causing harm to the targets. And that then it's the question how we are going to. There's no way other than currently then to remove the exit nodes, but or very much limit the type of traffic that is allowed to be originating from an exit node. I'm just wondering if there is any thought of how this technically bad traffic could be somehow isolated out of Tor.
Well, from the legal perspective, there is no easy answer to your question.
Well, Paolo maybe can help us.
Technical question.
Yeah.
If I can say something about this. So it's true that Tor is used for performing attacks. But in my experience and my understanding is that those who use Tor, for example, for SSH brute forcing or for other attacks, are normally people that don't have access to bigger resources for their attacks. Because if I had to implement an attack, I would probably prefer using botnets, which provides more nodes, more deployed, are more difficult to be discovered, because botnets basically use users' computer as attack vectors. So while the list of Tor nodes is publicly available, so it's much easier to detect attacks coming from the Tor network rather than attacks coming from a botnet. So if we had a way to block attacks from the Tor network, the attackers will probably just use other means, probably something like botnets or other available means, which might eventually actually make it a bit more difficult to detect. And but since the list of nodes is available, if you are confronted, for example, to a brute force attack, you can just impose limits on the amount of connection or that sort of technical countermeasures. But I don't know if this replies, but
yeah, it's a kind of a reply, I think. Yeah, I think it's better to protect from botnets than from Tor users that are using Tor to attack somebody. And okay, we can disagree.
Yeah, my point is that it doesn't distinguish from technical security point of view that the originator is a Tor node or is a broken computer. It is a source of malicious traffic, and unfortunately, that is something that needs to be eliminated.
In my understanding, I don't know if Paulo, you have the IP of Tor nodes, so you know all the nodes, so you can block them, whitelist it, if it's against some.
But the end user is expected to not receive any malicious traffic without any filtering. I mean, if it reports abuse, that this is SSH scanning node. Unfortunately, in some legislation, the action must be taken.
Okay, so we are coming to the legal aspect. So, is it legal for a country to DDoS or to attack in general? I mean, a European country. I'm not talking about East.
Yeah, okay, I would not call it an attack, maybe. Well, if the country decides to DDoS Tor, then it must have a pretty good reason to do that. And from the legal perspective, I don't really see the pretext for that.
Is it not against the rights that you presented?
It's yeah, it's definitely governments shouldn't do it. Yeah.
Okay, they should use other means, let's say.
They should try other means.
Other means. Okay. Do we have any other quick question? No? Okay, everybody's hungry probably for the dinner. Okay, so big applause to Thomas. Thank you. I know that you like this. I hope you will not plant any illegal things.
Thank you.